There are three basic types of synapses used to connect firing rate neurons. We'll be reviewing the gated synapse in this tutorial. The gated synapse is a modulatory synapse that acts like a basic switch. It's always associated with one or more other synapses that are entering the target neuron. So this is an axo-axonic synapse. In other words, it synapses onto the axon of the pre-synaptic neuron A instead of on the dendrite of the post-synaptic neuron B. Its function is to gate the pre-synaptic signal from neuron A to B. One way this can be accomplished in the real neuron is for neuron C to release a modulatory substance onto the axon from A to B that causes the axon to become strongly hyperpolarized. Then, even if neuron A is firing action potentials, when those reach the synapse, the hyperpolarization would short-circuit the spike and prevent calcium from entering the cell, which would prevent neurotransmitter from being released. Let's begin by opening a previous tutorial that we've already created. We'll open the normal firing rate neuron project, which is located at Program Files, AnimatLab, Tutorials, Neural Networks, Normal Firing Rate Neuron. Once it's finished loading, select the Save Project As item in the File menu and save this project with the name Firing Rate Gated Synapse. Now add 4 new neurons and rename them so that we have neurons 1 through 5. Set the memory capacitance of neuron 1 to 1 nanofarad. Gain to 10, and set the accommodation back to 0. Set the memory capacitance of neurons 2 and 4 to 1 nanofarad. Set the memory capacitance of neurons 3 and 5 to 1 nanofarad, and change their gain to be 20. Now add excitatory synaptic connections from neuron 1 to 2 and 4. Set the strength to be 5 nanoamps. Next, add a gated synapse from neuron 3 to 5. One of the most important properties of a gated synapse is the one that tells it which synapse it's actually gating. Click on the drop-down of the gated synapse value and it will provide you with a list of all normal synapses that are coming into the neuron that you're attempting to gate. This time there's only one incoming synapse from neuron 1, so select that one. We've now told this synapse to gate the excitatory connection from neuron 1 to 2. The gate can be either on or off by default. If it's on by default, then when neuron 3 fires, it will block the current of neuron 1 from entering neuron 2. In this case, firing of neuron 3 closes the already open gate. If neuron 3 is silent, then the current from neuron 1 is free to enter neuron 2. If the gated synapse is off by default, then this works in the opposite manner. When neuron C is silent, the gate is closed, and current is blocked from flowing from neuron A to B. When neuron C is active, the gate is open, and current can flow. This synapse will be off initially. The synaptic weight determines how much the gate closes or opens. The weight is multiplied by the firing frequency to determine the percentage of attenuation for the excitatory synapse. For example, our gate is initially closed. If we set the weight to 1, and if neuron 3 fires at its maximum rate, it will allow signals to pass from neuron 1 to 2 with no attenuation. If we set the weight to 0.5, and 3 fires at its maximum, it will allow only half the signal through. Set the weight to be 1. Add another gated synapse from neuron 5 to 4. Choose the incoming synapse from neuron 1 to gate. This time we'll do the opposite and set the gate to be initially on. Now, if neuron 5 fires, it will try and close the gate that's already open. To do this, we need to set the weight to -1. This way, when neuron 5 is firing at its maximum, it will completely block the signal from neuron 1 to 4. Next, let's enable the series of 5 stimuli and make sure that the stimulus to demonstrate accommodation is turned off. Then add a tonic stimulus to neuron 3. Set its start time to 550 milliseconds, end time to 850 milliseconds, and amplitude to 5 nanoamps. Add a tonic stimulus to neuron 5. Set its start time to 550 milliseconds, end time to 850 milliseconds, and amplitude to 5 nanoamps. Now let's create a new chart. Add 4 axes to show the currents and firing frequencies for each of our gates. Color coordinate the signals so you can tell them apart. Now run the simulation. In the top graph, notice how neuron 2 doesn't begin to fire even though neuron 1 is attempting to stimulate it. However, once neuron 3 also begins to fire, the gate between neuron 1 and 2 is opened and neuron 2's firing frequency picks up. Once neuron 3 stops, the gate is shut again. For neuron 4, the exact opposite happens. Stimulation from neuron 1 causes it to fire easily, but once neuron 5 begins firing, the stimulation is cut off and neuron 4 becomes quiet. Gated synapses are quite useful components for the firing rate neural system.